You know, it's kind of wild. Like our everyday experiences, they totally fall apart when you start talking about quantum mechanics.
Yeah, it's like our brains just weren't built for it.
Right. Like walking through a door expecting a hallway, but you end up in, I don't know, some crazy funhouse mirror situation.
That's a pretty good analogy.
Oh, it's what this whole deep dive is about, really quantum contextuality. We've got these two academic papers we're looking at.
And they are seriously interesting. What they basically say is that the results we see in quantum experiments, well, they might not just be determined by the system itself.
Okay, hold on. I think I'm with you.
It's like the context in which we measure something actually plays a role too.
Bizarre, right?
So it's not just about observing something that matters, it's the whole context surrounding that observation. Exactly. It throws a real wrench into our classical intuitions. Like that whole Schrodinger's cat thing, but even weirder.
Oh man, don't get me started on that cat. But I see what you're saying, kinda. So how does this context stuff actually work?
Well, imagine, right, that instead of just seeing if the cat's alive or dead, the outcome changes depending on if we looked in a totally different box first.
Wow, okay.
As if measuring one thing can somehow influence another, even if they seem totally unrelated.
Mind bending.
That's quantum contextuality in a nutshell.
So where do these papers you mentioned come in?
Well, the first one uses this thing called a quantum harmonic oscillator to explore this idea.
Okay, before we go any further, can we back up a sec? What exactly is a quantum harmonic oscillator? It sounds kind of intimidating, not gonna lie.
Sure, sure. Think of a kid on a swing, back and forth, back and forth. That regular motion, that's oscillation. And it's everywhere. Pendulums, guitar strings, you name it.
Gotcha. Simple enough.
Now take that simple motion and apply quantum mechanics to it. That's basically your quantum harmonic oscillator.
So we're taking something that seems predictable, like a pendulum, and then dot bam, quantum weirdness.
Pretty much.
Yeah.
This first paper, they used this new mathematical framework, right? And guess what?
They found our pendulum suddenly decided to defy the laws of physics.
Uh-huh, kinda. They showed that even in a system that seems simple, you can get different outcomes depending not just on what you measure, but on how you measure it. It's all about context.
Okay, so it's not just cats and boxes anymore. Now pendulums are messing with reality too.
Exactly. And this is just the beginning. The second paper takes things even further, talking about something called state-independent contextuality.
Now we're getting to the really weird stuff. Does this mean it's not even about the thing itself being strange, but reality on a fundamental level?
You got it. This second paper shows that no matter what, some properties of quantum mechanics just won't ever fit with our regular classical view of the world. Like they found specific measurements that constantly go against our normal ways of thinking.
It's like that survey analogy you used earlier, only way weirder. No matter how you arrange the questions, the answers still come back making no sense.
Precisely. And that's why this paper is so fascinating. It hints that this contextuality isn't just some random quirk. It might be built into how reality itself works.
Wow, okay, my brain needs a minute to catch up. So we've gone from cats and boxes to basically questioning the fabric of reality. Can we maybe bring it back to something a little easier to grasp? The first paper also mentioned coherent and squeezed states of light, right? Like lasers.
Right. And these states are perfect examples of how this stuff isn't just theoretical. It pops up in the most unexpected places.
So you're telling me that even the light we use every single day, fiber optic cables, all of it is secretly playing by these bizarre quantum rules. What makes coherent and squeezed states so special anyway?
So coherent states, think of them like the most normal kind of light you can get.
Normal by quantum physics standards, you mean?
Exactly, like a perfect laser beam. Yeah, all the light waves are basically marching in sync.
Okay, so even our most organized light still has a little quantum chaos hidden inside.
You got it. Even when it looks classical on the surface, it's still following those quantum rules underneath.
And what about those squeezed states? Those sound even weirder, honestly.
They are pretty wild. Imagine you've got a balloon, right? You squeeze it, what happens?
It changes shape, gets longer or wider in one direction, but then flatter or narrower in the other.
Bingo. Squeeze light is kind of like that. We can manipulate it so certain properties get super precise.
But then other properties get more uncertain, like a trade-off.
You got it. It's like playing a game of quantum give and take with the light itself.
Okay, so this is blowing my mind already, but I still want to connect the dots back to contextuality. Are you saying our lasers, our fiber optic cables, that stuff is also affected by this whole context thing?
100%. That's what's so cool about that first paper. It shows that both coherent and squeezed states can be contextual. how we measure them actually changes the results we get in ways that just wouldn't make sense if the world was purely classical.
It's like the light is being forced to pick a reality, but the way it picks depends on how we're looking at it.
Exactly. It really throws a wrench into those classical intuitions.
No kidding. Okay, I'm starting to see the bigger picture. This isn't about cats or pendulums. It's about how we understand measurement and observation in the first place, right? Like on fundamental level.
That's it. And what's even more interesting is how this ties into the second paper. Remember we talked about continuous variables?
Yeah, we kind of glossed over that. Can we dive into that a bit more? What are they and why do they matter here?
Of course. So far, we've mainly been talking about systems with like distinct states. The kid on a swing, they're either at this point or that point, right?
Makes sense.
But tons of stuff in the quantum world, it doesn't act that way. Think of a light dimmer.
Okay.
You can make it brighter, dimmer, anywhere in between, smoothly, yeah. Practically infinite brightness levels.
Ah, I see where you're going with this.
That brightness, that's a continuous variable.
Yeah.
You've also got position, momentum, even like the phase of a wave, all continuous variables in quantum mechanics.
So it's not just an on-off switch. It's like a dimmer with a whole range.
Exactly. And what that second paper suggests is that these continuous variables, they're deeply tied to contextuality too.
So it's not just about these simple states and measurements. Even the more, I don't know, fluid parts of reality are playing by these weird contextual rules.
It seems so. The math gets pretty intense, but the basic idea is that just trying to measure a continuous variable to pin it down, that act itself is wrapped up in this contextuality.
So even in the smoothest, most continuous aspects of the quantum world, we still run into this wall. Just by looking at something, trying to measure it, we're already influencing it.
You got it. And that, my friend, is a huge challenge to our classical ideas about cause and effect.
Yeah, no kidding. If just measuring something is affected by how we observe it, then what does that even mean for the nature of reality itself? It really makes you wonder, about like everything we think we know about how things actually work.
It's true. And it's not just, physicists who should be paying attention. This stuff goes way beyond that.
Right, because it's about the universe at a fundamental level. But okay, let's bring it back down to Earth for a sec. For those of us who aren't, swimming in quantum equations all day, why does any of this matter?
Well, I think the biggest takeaway is this. Reality.
Mm.
Yeah, it's probably even weirder than we ever imagined.
Okay, I can get behind that.
Like, our brains, they want to say, the world exists, we exist, end of story. But quantum contextuality, it's like it's saying, nope, not so fast.
Because just by looking at something, we're changing it.
In a way, yeah. The very act of observing, of measuring, he can actually influence what we're trying to measure.
So we're not just these passive observers anymore. We're practically participants in creating reality.
Kind of, yeah. And while that might seem, I don't know, completely mind-blowing right now, it could totally change everything.
You mean like practically? What kind of changes are we talking about?
Think about it. Quantum computers, new ways of encrypting information, even understanding the universe itself in ways we never thought possible.
So it all starts with these crazy quantum ideas, and then bam, it's changing our technology, our understanding of, well, everything.
Pretty much. It's a whole new frontier out there.
Makes you realize how much we don't know.
Exactly. And that's what makes it so exciting.
To think it all started with questioning, like, the most basic stuff we thought we knew about the world.
And look where we are now. There's a whole universe of mysteries out there just waiting for us to figure them out.
Well, on that note, I want to thank everyone for joining us on this wild ride through quantum contextuality. It's been,
An adventure.
to say the least. But seriously, to everyone listening, keep asking questions, keep being curious, because who knows, maybe that's part of what shapes the reality we live in.